there was some technical issues with the old link. That's why I shared the new link. So I think within some time, some more people will join. So let us begin the session for today. And in between, if you are facing any technical glitches, please let me know. And today we will cover the week 8 session of the introduction to abstract and linear algebra. So first we will go through the basic concepts and then we will solve some of the problems. So let me share the screen first. Is my screen visible?
Yes, ma'am.
Okay. Yeah, actually, sorry for the delay and the technical problem. I couldn't start on time. There was some meeting passcode it was asking, and actually there was no meeting passcode. And also with this Zoom link also, there can be sometimes like after 40 minutes it may stop. So please join the Zoom meeting again, once again. So if some problem is there, please let me know through the messages or just unmute and tell, okay? So let's start today's session.
Yes, ma'am.
Okay. So in the last week, actually, we have seen eigenvalues. So in week 8, so this is the last week. So in week 8, we have seen eigenvalues, eigenvectors, and what is the characteristic polynomial, and what are the geometric multiplicity, algebraic multiplicity of the eigenvalues. So let's start with some of the concept that we have covered in this week. So what is a characteristic polynomial?
A minus lambda I.
Yeah, a minus lambda I.
Lambda I equal 0.
Yeah, determinant of a minus lambda I equal to 0. So,
Lambda I equal.
yeah, so this is the characteristic polynomial, or this is the characteristic equation actually. So, this is the characteristic equation. There is an equality, so it is the characteristic equation. Okay, so roots of the characteristic equation are called eigenvalues. Okay. Okay, any doubt? So it will be, if A is an n by n matrix, okay, then it will be a n by n degree n polynomial, and the root of that polynomial is called characteristic eigenvalues. Okay, that polynomial is called characteristic equation, and the roots are called eigenvalues. Now we have learned the determinant equal to and trace. Okay, if A is a metric and we got the eigenvalues. So how can we write the determinant of A in terms of these eigenvalues? Can anyone tell?
Product of eigenvalues.
Yeah, determinant of A is the product of eigenvalues. And the trace of A?
Sum of the eigenvalues.
Trace of A is the sum of eigenvalues. So this will be the one of the result we will be using in so many problems. Okay. And the third result is, if A is non-singular metric, and lambda is an eigenvalue. Okay. First question is, can lambda be a 0? A is non-zero.
No, ma'am.
Okay, then lambda is non-zero. So what the result says is, then 1 by lambda is an eigenvalue of A inverse. Okay, if A has eigenvalue lambda and A is non-singular, then lambda inverse is an eigenvalue of A inverse. Now the next result is, if A is an n by n matrix, and P is non-singular, then A and P inverse AP has same eigenvalues. If A has lambda 1, lambda 2, etc., lambda n has the eigenvalues, then P inverse AP also has the same lambda 1, lambda 2, etc., lambda n as the eigenvalues. Has same eigenvalues as A. Clear? Okay, the proof and all, actually it is covered in the class itself. So you can go to the proof and all. Just we are going through the result so that we will use in the problems later. Now, what is an eigenvector? We are going to eigenvector. Can anyone say what is an eigenvector?
A non-zero vector that satisfies the equation Ax equal to lambda x,
Correct.
where A is the square matrix.
Yeah, if A is a n by n, say it is a square matrix of order n by n, and if x is non-zero, x is non-zero means it is x equal to, we can say x1, x2, etc., xn. Okay, it is a non-zero vector. Okay, such that Ax equal to lambda x for some scalar lambda. In this case, we say x is an eigenvector corresponding to an eigenvalue. To eigenvalue lambda. Okay, corresponding to this eigenvalue lambda, x is the corresponding eigenvector. Okay. Now, if x is an eigenvector, its eigenvalue lambda is unique. So what does this means is, it is not possible that Ax equal to some lambda 1 x and Ax equal to lambda 2 x for lambda 1 not equal to lambda 2. That is, for distinct lambda 1 and lambda 2, Ax equal to lambda 1 x and Ax equal to lambda 2 x is not possible. This is what this result says. Clear? And also, we have already seen what is an eigenvalue. Lambda is an eigenvalue. Okay. So, corresponding to each lambda, there exists an eigenvector. If lambda is an eigenvalue, that means lambda is the root of the characteristic equation. So, what we have is determinant of a minus lambda equal to 0. Okay. So, obviously, like a minus lambda is a singular matrix. So, there exists a non-zero x, lambda into x equal to 0 for some non-zero x. Okay. So, like if we are starting with any eigenvalue, that is the root of a characteristic equation, we can find an eigenvector associated with that eigenvalue. Okay. So, this is the what exactly this eigenvalue and eigenvector and how they are related and all. Okay. Corresponding to each eigenvalue, there exists at least one eigenvector. Maybe more than one eigenvector is also possible. Okay. But corresponding to one eigenvector, the corresponding eigenvalue is unique. So, that is what we have seen in this above. Okay. Is there any doubt until now? Now, if x is an eigenvector corresponding to lambda, then Cx is also an eigenvector for C not equal to 0. Okay. What here it is saying is x is an eigenvector corresponding to lambda. That means Ax equal to lambda x. So what we want to prove that Cx is also an eigenvector. This is obviously false because Acx equal to, we can write it as lambda Cx. Correct? Acx, we can take this. Okay, Acx, we can take it as C times Ax, which is C times lambda x or lambda times Cx. Okay. Now, the next important result is if lambda 1 not equal to lambda 2 are eigenvalues for A. We are taking a matrix A and lambda 1 and lambda 2 are two distinct eigenvalues. Then corresponding to lambda 1, we have x1 as an eigenvector. And for lambda 2, we have x2 as an eigenvector. Okay. Then this x1 and x2 are linearly independent. What does this mean? Corresponding, the eigenvector corresponding to distinct eigenvalues are linearly independent. Okay. So this we are writing for two eigenvalues and two eigenvector. But if we are extending it to an n case, like if lambda 1, lambda 2, etc., lambda n are eigenvalues for A and x1, etc., xn are corresponding eigenvectors for this lambda i's, then x1, x2, etc., xn will be a linearly independent set. Okay. Now, what is an eigenspace or characteristic space? Can anyone say what is an eigenspace? So V lambda means the eigenspace corresponding to the eigenvalue lambda. What is this? This is the set of pole x such that Ax equal to lambda x. Okay, this is actually a vector space. It's a subspace of Rn, x coming from Rn, since A is an n by n matrix. So this V lambda consists of set of all x in Rn such that Ax equal to lambda x. Set of all x in Rn such that Ax equal to lambda x. Okay, so here actually we can say this consists of all the eigenvector, that is Ax equal to lambda x. If x is non-zero, then we say it is an eigenvector. And in the other way, we can say if x is 0 also, A0 equal to lambda 0. That means 0 also belongs to this set V lambda. So this V lambda is actually consists of set of all eigenvectors and the 0 vector. Okay, so the inclusion of the 0 vector also makes this a vector space. So 0 belongs to V lambda. Okay, and we have already proved that if x belongs to V lambda, then Cx also belongs to V lambda. Okay, that we have seen. And in the other way, if x and y belongs to V lambda, we can see that x plus y also belongs to V lambda. So this you can just work it out. If x and y belongs to V lambda, then y x plus y belongs to V lambda. So, and all the other properties of a vector space will be satisfied. Okay. So it is a vector space. The eigenspace is a vector space. Okay, now algebraic multiplicity of lambda. And the geometric multiplicity of lambda. So what is this algebraic multiplicity and geometric multiplicity? Anyone knows what is algebraic multiplicity? So, okay, let me explain. The algebraic multiplicity of lambda means the number of times the factor x minus lambda, so comes in characteristic equation. So we have a characteristic equation, determinant of a minus lambda equal to 0. So we will factorize it. So if P of x is the characteristic equation and lambda is an eigenvalue, we can write it as x minus lambda power some r into some phi of x. Okay, we are taking the factor x minus lambda, like the maximum of x minus lambda power r outside. So whatever this r comes here, that r is the algebraic multiplicity. Okay. Now, geometric multiplicity of multiplicity of lambda means the dimension of eigenspace of lambda. Okay, so we already got the lambda and the eigenspace of lambda as above. Okay. What is the dimension of that vector space? That is the geometric multiplicity of lambda. And one of the important result is, so here in the lecture, it is done without proof. The proof is not so difficult, but we can omit the proof as of now. It says that the geometric multiplicity of lambda will always be less than or equal to algebraic multiplicity of lambda. And the geometric multiplicity of lambda is at least 1. It is bounded below by 1 and above by algebraic multiplicity of lambda. Okay. Now, in any case, if you are getting algebraic multiplicity as 1, we can conclude geometric multiplicity is also 1 using this result. Okay. Now, let me go through some of the standard result. The first one is the eigenvalues of real symmetric matrices are real. Okay. Real symmetric matrix means A equal to A transpose. A is a real matrix and it is A equal to A transpose. In this case, the eigenvalues of this metric will always be real values. Like it cannot be complex or any other number. It is always real. And the second one is eigenvalues of Q symmetric matrices are either purely imaginary or 0. So what is Q symmetric matrix? What is Q symmetric matrix means? This A equal to minus A transpose. If A equal to A transpose, it is symmetric metric. And if A equal to minus A transpose, it is skew symmetric metric. Okay, one more thing. Here it is real skew symmetric metric. Okay. Any doubt? Anyone? Is there any doubt? Okay. So let me go to the next result. What is a similar matrix? If A is a matrix, A is an n by n matrix, and B is also an n by n matrix. Okay, when will we say this A is similar to B? When can we say A is similar to B? A is similar to B if there exists P invertible such that B equal to P inverse.
P inverse of A.
Yeah, if B can be written as P inverse of AP, then we will say A and B are similar matrices. And one thing is, if A is similar to B, on the other hand, we can say B is similar to A also. Okay. So in the same way, we can prove reflexive, symmetric, and transitivity property. So this similar matrices. Sorry, similarity is a equivalence relation. Okay, it satisfies the reflexive, symmetric, and a transitive property. Clear? And the next result is, if A is similar to B, then eigenvalues of A and B are same. Okay, if A is similar to B, eigenvalues of A we will find maybe lambda 1, lambda 2, etc., lambda n. And this B also will have the same eigenvalues. But this is not true for eigenvector. The eigenvector of A and eigenvector of B need not be same always, even though they are similar. But in case of eigenvalue, they are same. But the converse is not true here. So what is the converse? Here, what is the converse?
Eigenvalue of B is need not be eigenvalue of A.
Yeah, converse says that if eigenvalue of A and B are same, then A is not A need not be similar to B. That means if A and B has
Same eigenvalue.
same set of eigenvalues, then A need not be similar to
B.
B. Okay, so this is the next result. Now, what is diagonalizable? When will we say a matrix A is diagonalizable? A matrix A is diagonalizable if A is similar to a diagonal matrix B, where D is a diagonal matrix. Or we can say A equal to some P inverse dP for some metric P. Okay, some matrix P. If this is satisfied, we will say A is diagonalizable. If A is similar to a diagonal matrix, then we will say A is diagonalizable. Clear? Now we have some results regarding this diagonalizability. Suppose A is similar to D and this D is written as lambda 1, etc., lambda 1. So the diagonal matrix means only the diagonal entries are some can be non-zero, all others are 0. So in this case, can you say what are all the eigenvalues of A?
Lambda 1, lambda 2.
Yes, the eigenvalues of A are
Lambda 1, lambda 2, etc. lambda n.
lambda 1, lambda 2, etc., lambda n. The reason is D is diagonalizable, sorry, A is diagonalizable and A is similar to D. And D is the diagonal matrix with the diagonal entries lambda 1, etc., lambda n. So obviously the eigenvalues of D are lambda 1 to lambda n. And since A is similar to D, A and D have same eigenvalues. So A also have the same eigenvalues as that of D. And so the eigenvalues of A are lambda 1 to lambda n. And the next result is A is diagonalizable if and only if there exists Okay. If there existed n linearly independent eigenvectors, A is an n by n matrix, and if it has n linearly independent eigenvectors, it is diagonalizable. On the other way, if it is diagonalizable, it will have n linearly independent eigenvectors. So this is a necessary and sufficient condition. Okay, before going to the next result, again, this Zoom meeting may end within 2-3 minutes. So I just want you to join again. I want to continue the class till 9. So please, everyone, even though if it ends, please everyone join back to the same link. So we will have the class again. So until it stops, we will proceed. So please join again. Okay, so let me go to the next result. So now again, A is an n by n matrix. It is diagonalizable. Now we are giving an if condition. Earlier it was an if and only if condition. Now, if some condition is satisfied, then it is diagonalizable. A is diagonalizable if A has n distinctive eigenvalues. Okay. So what it says is, if A has n distinct eigenvalues, say lambda 1, etc., lambda n, corresponding to each of this eigenvalue, we will have n linearly independent eigenvectors. That means corresponding to each eigenvalue, we have one eigenvector. Okay. So lambda 1, lambda 2, etc., lambda n are the eigenvalue. So corresponding to each of it, we have x1, x2, etc., xn as the eigenvector. Okay. Obviously, these are corresponding to distinct eigenvalue. So these will be linearly independent. So what we are getting is we have an n linearly independent set of eigenvectors. So what we can say using this condition, A is diagonalizable. So from this we can go to this condition. So we can say A is a diagonalizable matrix. Now the next thing is, okay, so I think that's all for this. So these are all the things covered in the last week, that is week 8. Okay. Now we will go to the questions. So the first question is, the matrix A is given 4, 1, 1, 4. So we need to find the eigenvalues of this matrix. So the options are given as, first is 3, 5. So a matrix is given and the question is to find the eigenvalues of this matrix. Okay. So just by looking at this, you can say like one thing is to find the characteristic equation, solve the equation for the roots to get the eigenvalue. One is that way. Other than that, using any of the results we stated above, can we say very quickly what are all the eigenvalues of this matrix?
Four and 1 month.
So, okay, I will give one hint. Sum of eigenvalues and product of eigenvalues. What is sum of eigenvalues? Yeah, option A. Yeah, option A is the correct answer. So the very quick way to answer this is to check the sum of eigenvalue and the product of eigenvalue. So the sum of eigenvalue equal to trace of A, and product of eigenvalue is determinant of A. Here the trace of A is the sum of diagonal entries. Okay, 4 plus 4, which is equal to 8, and determinant of A is 16 minus 1, which is equal to 15. So from this option, only 3 and 5 is possible. 3 plus 5 is 8, and 3 into 5 is 15. Okay. So from this, we can say option A, 3, 5 are the 3, 5 are eigenvalues. Okay, so we will do as usual, that is determinant of A minus lambda equal to 0. Using that also we will find. So the meeting is going to end in 1 minute. So please, is the screen visible now?
Yes, ma'am.
Okay, sorry for this technical problem. Actually, the subscribed Zoom version is not here, I think. So anyhow, we will have to, after 40 minutes, we will have to re-log in once again. Okay. Let me proceed with this question. So here for this question, we will do this using the equation like determinant of A minus lambda equal to 0. So we will solve once the problem, so that you will get to know how it comes. Okay. So what is A is 4, 1, 1, 4. Okay. So A minus lambda I means lambda 0, 0 lambda. So what we want is determinant of this should be equal to 0. So this is okay. So determinant of this should be equal to 0, and we can write it as determinant of 4 minus lambda 1, 1, 4 minus lambda. So this is just the calculation. Okay, so our characteristic equation, we got it as lambda square minus 8 lambda plus 15 equal to 0. And from this we can solve lambda for lambda equal to 3 and lambda equal to 5. So these two are the eigenvalues. So now the question is, what is the eigenvectors? Okay, before going to the eigenvector, let me ask one question. What is the algebraic multiplicity of lambda equal to 3? So lambda equal to 3 is one eigenvalue. Okay. So the question is, what is the algebraic multiplicity of 3? So by definition, what is the algebraic multiplicity?
1.
Okay, so the answer it is given here 1. Correct. So algebraic multiplicity means how many times this lambda minus 3 repeats. I mean, how many times it is a factor. Here it is only one time it is a factor. So algebraic multiplicity is 1. And what is the algebraic multiplicity of 5? 1. Again it repeats. The factor lambda minus 5 comes only one times in the characteristic equation. So the algebraic multiplicity is 1. Now we will find the eigenvectors corresponding to lambda equal to 3 and lambda equal to 5. So first we will start with the eigenvector corresponding to lambda equal to 3. Okay. So we need a non-zero x such that ax equal to lambda x. Okay. Then such an x is said to be the eigenvectors corresponding to lambda equal to 3. Otherwise what we can write? A minus lambda x equal to 0. This is actually a is 4 1 1 4 and x is x1 x2 same. Okay. And lambda here we are taking lambda is 3. So this matrix into x1 x2 should be equal to 3 times x1 x2. Okay. We need to find the value of x1 x2 such that it is satisfied. So we will write this equation as a minus lambda I x equal to 0. So here a minus lambda I means a is 4 1 1 4 and lambda is 3. So lambda I means 3 0 0 3. Okay, I will write 4 1 1 4 minus 3 0 0 3 into x1 x2 equal to 0. This is the equation we need to solve. Okay. Now here we will get it as 1 1 1 1 1 into x1 x2 equal to 0 0. So this is actually x1 plus x2 equal to 0 or x1 equal to minus x2. This actually you can see this is actually a vector space, like the line y equal to minus x. Okay. So this is actually a vector space. So the eigenvector will be in the form x1 minus x1. So x2 is minus x1. So I can write it as x1 minus x1, or in particular if I am giving say a value 1. Okay. Then 1 minus 1 I will get as an eigenvector. So you can just check this 1 minus 1 in the above. Okay. So here what we are having is 4 1 1 4. The obtained x1 x2 is 1 minus 1. Okay. So if we are putting 1 minus 1 here and 1 minus 1 here, you will see this is actually true. Okay. So we got one eigenvector corresponding to this lambda equal to 3. Now the question is there any eigenvector corresponding to lambda equal to 3 and which is linearly independent to So the question is there any eigenvector corresponding to lambda equal to 3? For lambda equal to 3, we have found one eigenvector 1 minus 1. So is there any linearly independent eigenvector corresponding to lambda equal to 3? Any answer? Okay, before going to this answer, what is the geometric multiplicity of 3? So someone has written, yeah, no, because we have characterized all the eigenvector corresponding to 3 as x1 minus x1. So just one x1 minus x1 or 1 minus 1 is enough to generate whole eigenvector. Okay. So the whole eigenvector is generated by just one element. Okay, just this one element generate the whole eigenvector. So what is the eigenspace corresponding to this lambda equal to 3 dimension of eigenspace? It is generated by this one element 1 minus 1. Okay, so this is the dimension of the eigenspace. So the dimension of the eigenspace corresponding to 3 is said to be the geometric multiplicity. Okay, so this geometric multiplicity is equal to 1. Is this clear? Is there any doubt why this geometric multiplicity is 1? Is this clear, this geometric multiplicity?
Yes, ma'am.
Okay, okay. So, again for lambda equal to 5. Okay, lambda equal to 5 is the next eigenvector. So, what we need to find is 4, 1, sorry. 4, 1, 1, 4 minus lambda I. X1, X2 should be equal to 0, 0. So we need to solve this system. Again, we can see it as minus 1, 1, 1, minus 1, X1, X2 equal to 0. So this says that minus X1, this is just calculation. So what we can say is set of all x1, x2. Okay. Set of all x1, x2, sorry, x1, x1, such that x1 in R, it is the eigenspace corresponding to lambda equal to 5. Okay, here I have given one particular example, 1, 1 as the eigenvector. Okay, and the whole space is generated by, like it is written as set of all x1, x1 such that x1 in R. Okay, so here again, what is the geometric multiplicity of 5? The dimension of eigenspace corresponding to 5, and it is 1 because it is just generated by only one element. Okay, this 1, 1, 1 spans whole eigenspace and it is linearly independent. So the dimension of this space is 1, and that is the definition of our geometric multiplicity. So it is 5. Okay, so from here also you can see 1 less than or equal to geometric multiplicity of lambda less than or equal to algebraic multiplicity of lambda. Actually, here both are equal. Algebraic multiplicity and the geometric multiplicity are 1. It need not be true always. Okay. So now let's go to the next problem. Let the eigen values of a 3 by 3 invertible matrix is lambda 1, lambda 2, and lambda 3.
Ma'am,
Yes.
Ma'am, can we find the eigenvalue converting our matrix into triangle or upper triangle or lower triangle?
Can you repeat the question? Converting means you are saying the similar to upper and lower triangle.
Yes, ma'am.
To find the eigenvector. Actually,
No, ma'am. To find the eigenvalue.
yeah, that you can do because eigenvalues of this similar matrices are same. If you are finding a similar matrix, like here we have 1 4 4 1. If you are finding that to a similar matrix, which is like diagonal, upper triangular or something, whatever. So you can find the eigenvalue of the corresponding matrix, and then you can conclude that that is the eigenvalue of the original matrix.
Okay, ma'am. Okay.
Now, okay. So here, the invertible matrix A. Okay. So the question is, given an invertible matrix A and its eigenvalues are given as lambda 1, lambda 2, lambda 3. So what are the eigenvalues of A inverse?
One by lambda 1, 1 by lambda 2, 1 by lambda 3.
Yeah, we have already proved, like we have already shown that result. If A has an eigenvalue lambda, then 1 by lambda is an eigenvalue of A inverse, correct? So the answer is 1 by lambda 1, 1 by lambda 2, 1 by lambda 3. So we got 3 eigenvalues, and the A inverse is also a 3 by 3 matrix. So we got the 3 eigenvalues of the 3 by 3 matrix. Are the eigenvalues of A. Okay. So anyone wants the proof of this? So this is already stated result. So anyone needs the proof? If any of you want the proof, we can go very quickly. It's a very simple proof. Okay, we'll just very quickly go through the proof. So what we want to prove that if lambda is an eigenvalue of A, then lambda inverse or 1 by lambda is an eigenvalue of A inverse. A is invertible. Okay, this is the statement we need to prove. If lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. So, since lambda is an eigenvalue of A, what we can say? Determinant of A minus lambda equal to 0. Okay. So, usually we will solve like determinant of A minus xi. So, this is our okay. See here, determinant of A minus xi. So this is our characteristic polynomial. So what are all the roots? Okay, that is our eigenvalues. So at the eigenvalue, if lambda is a solution of this characteristic equation, what we can say? This determinant of A minus lambda equal to 0. Okay. At that particular value lambda, this equation or this polynomial vanishes because it is the root of that polynomial. Lambda is a root of the polynomial. Here also lambda is an eigenvalue of A means lambda is a root or 0 of the polynomial determinant of A minus xi. Okay, that means determinant of A minus lambda equal to 0. Now, we need to prove that lambda inverse is a root of determinant of A inverse minus 1 by lambda I. Okay. We need to prove that lambda inverse is an eigenvalue of A. So we need to prove that lambda inverse is a root or 0 of the polynomial determinant of A inverse minus 1 by lambda I. So what we want to prove, this is equal to 0. Okay. So the thing what we are having is determinant of A minus lambda equal to 0. And we need to prove this is equal to 0. So what we will do is, here we will just use the properties of determinant. Okay. We are taking the A inverse outside. So what we will get, I 1 by lambda A. Okay. Here I can write it as A inverse into A, and I am taking that A inverse outside. So here we will get like this. Okay. Now this is determinant of A inverse into determinant of I minus 1 by lambda A. Okay. So determinant using the property, we can split it like this. Now, determinant of A inverse, let it be there. Here I am taking minus 1 by lambda outside. So since A is an n by n matrix, always we are assuming A is an n by n matrix into determinant of A minus lambda I. Okay. So minus 1 by lambda we are taking outside. So A will come here and minus I, and to compensate this lambda here, we have 1 lambda here. Okay. Now what we know is this value is 0. Determinant of A minus lambda is 0. Okay. So the whole value is 0. So we got 1 by lambda is a solution of the polynomial determinant of A inverse minus 1 by lambda I. Okay. This implies 1 by lambda is an eigenvalue of A inverse. Fine. Is that clear? So this is already covered in the class, actually, the proof also. So the proof is very simple. If you have any doubt, you can ask. Shall we go to the next problem? Okay. So the question is, we are given a characteristic polynomial, okay, of some matrix. The matrix is not specified. I mean, which order, it is not specified. And the question is to find the order of the matrix by checking the characteristic polynomial. Okay. So this is the characteristic polynomial, lambda minus 1 into lambda minus 3 square into lambda minus 4 cube. Okay. So what is the order of the matrix? Order of the matrix means is this n by n by m, like that we will say, right? So is that 5 by 6 or 5 by 6 by 5 or 6 by 6 or 5 by 5? Okay, first of all, can it be A or C option? Can it be A or C? A means 5 by 6 matrix. Okay, option B is the correct answer. So it cannot be A or C. First of all, how the characteristic polynomial is defined? Determinant of A minus xi or A minus lambda equal to 0. Correct? Here, the determinant is applicable only for square matrix. Okay. So the characteristic polynomial means determinant of A minus lambda equal to 0. Okay. So, obviously, the 5 by 6 or 6 by 5 is not possible because to find the determinant, it should be a square matrix. Clear? Now, the option, someone is saying the option B is the correct answer. Option B means 6 by 6. Okay. So, 6 by 6 is correct because we can say that if A is an n by n matrix, the characteristic polynomial is of degree n. Okay. What we are doing? Determinant of A minus lambda. So, if it has 6 rows and 6 columns, so we have 6 times lambda. Along the diagonal, we have some lambda minus some 1, lambda minus 3, something like that. Okay. So, what we are doing is finding the determinant. So, this lambda is repeated 6 times, multiplying 6 times. Okay. So, the power of lambda is the order of the matrix. Here we can say it is lambda minus 1 into lambda minus 3 into lambda minus 4 cube. So here the degree of here we can see degree is 6, 2 plus 3 plus 1. Okay. So degree of P of lambda equal to 6 means the matrix has size or order 6. Okay. Any doubt in this question? Anyone is having doubt? Mm. So the next question is, so A is an n by n matrix is given. And suppose A has rank n. Okay. So the options are TA is not 1 to 1 and lambda equal to 0 is not an eigenvalue of A. The range of TA is 0 and the kernel of TA is R. So what is the correct option? Okay, here we will slowly start. Okay, second option. So we will see why the second option is correct and why all other options are wrong. Okay, here rank of A equal to n. So can you think about the rank nullity theorem? How can you use the rank nullity theorem here? What is rank of A plus? Okay.
Rank of A plus nullity of A is equal to dimension of A.
Yes. Rank of A plus nullity of A equal to dimension of A. Here it is given an n by n matrix. So here also it is given rank of A equal to n. Okay. So what does this mean? What is nullity of A? Nullity of A equal to 0, right? Because rank of A plus nullity of A should be equal to n. So nullity of A equal to 0. Now, the map is given TA. What does this TA means? TAX means AX. Okay. So TA is just defined as TA of x equal to AX. That is what is meant by the linear transformation TA. So whatever applicable for A, it is applicable for TA also. That means if A has rank n, then TA has rank n. And if A has nullity 0, then TA has nullity 0. That means kernel is 0. Okay. Now,
Ma'am,
yes.
ma'am, nullity is the dimension of null space, right?
Which is the dimension of null space? Nullity, yeah.
Yeah, yes, ma'am. So, if determinant is not equal to 0, so our matrix will never be a null matrix, right?
Yes. Here rank equal to n and nullity equal to 0 means determinant is non-zero, correct?
Okay, okay, ma'am.
So determinant is non-zero. So, okay, we can say determinant is not equal to, determinant of A not equal to 0 or A is invertible. Okay. So, A is an invertible matrix and TA is the corresponding transformation. TA of x equal to AX. Okay. So, can the kernel of TA is, can TA is 1, 1? No, right? This TA is invertible. Invertible means A is invertible. Invertible means TA should be 1, 1 and 1, 2. Correct?
Ma'am, what's TA here?
TA is AS. Like this. Means TA is a linear transformation which map TA of x1, x2, etc. is defined as A into x1, x2, etc.
Okay,
Okay.
ma'am.
So whatever we are saying for A, it is the same for TA also. You can see it like that. Okay. So here A is an invertible matrix. Rank of A equal to n. Okay. Or we can say rank A equal to n means range of A. Rank of A n means range of A has dimension n. Okay. It has dimension n means it should be the whole Rn, right? Okay. Dimension n means it should be whole Rn. So range of A is Rn or range of TA. A means TA only. The range of TA is 0. This is false because range of TA is Rn. Okay. And also we have TA is 1, 1 and 1, 2 map. Since A is invertible, there exists a unique element which is mapping to some unique element. Okay. A, X is unique. That means TA of X, we will say AX equal to Y. And this X is actually A inverse Y. Okay, if we have one x here, we can determine y uniquely as ax equal to y. In the same way, for any y if we are taking, we have a unique x here. So this dA is actually 1, 1 and on 2. Okay. So going to the options. So we got TA is 1, 1 and on 2 because A is an invertible map. So TA is not 1, 1. This is wrong. Okay. And the range of TA is 0. That is also wrong because range of TA is complete Rn. We found that rank equal to n. So rank is the dimension of range. Okay. So here the dimension of the 0 is 0. Okay. Dimension is of range is n means it should be Rn. So this third option is also wrong. And the kernel of TA is Rn means the null space of TA is Rn. It is false. If null space is Rn, then the nullity will be n. But here we got, since rank is n, nullity is 0. Okay. So this kernel cannot be Rn. Correct? So this is also wrong. Now, coming to option second, it is correct obviously because we got A is a invertible matrix. It has rank n means we can say it is invertible. So if it is invertible, its determinant is non-zero. That means this lambda is not an eigenvalue. See, if lambda is an eigenvalue of A, lambda equal to 0. If lambda equal to 0 is an eigenvalue of A, we can say that A minus 0y, lambda is 0. Okay. Sorry. Determinant of A minus 0 equal to 0. But that means determinant of A equal to 0. This is not true because since rank A equal to n, rank A equal to n, so the determinant of A cannot be 0, correct? So option B is the correct answer. Is every option clear? Is there any doubt?
Ma'am, please repeat first option.
Okay, first option. See, rank of A is n means A is invertible. That is fine, right? Okay. Rank of A equal to n. That means A invertible. Okay. So, now, okay. Our map is TA of x equal to AX. Our question is TA 1, 1 or on 2? So, is TA 1, 1 map? Okay, that is the first option. First option says TA is not 1, 1. Okay. Now we are checking whether TA is 1, 1 or not. So, how we will say it is 1, 1 or not? TA of x equal to TA of y implies x equal to y. Then it is 1, 1. Okay. Now, what is TA of x? It is AX. This is AY. Okay. Now, I am applying, since A is invertible, I can, okay. Okay, before going to that, this meeting again will end in 1 minute. So, I request you all to join once again. So, one more 40 minutes we will take, and after that we will stop. So, we will do some more questions. So, please join again. It will end soon. Okay, I will go to this question, remaining part after that. Okay, let me proceed. So, AX equal to AY. So, we can say that we are just multiplying A inverse on both sides. So A inverse A is identity.
Yes, ma'am.
Okay. Okay. So what we were saying is why TA is 1 1. Here TAX equal to TAY. So that implies AX equal to AY. Okay. And we are multiplying with the A inverse on both sides. And finally we will get X equal to Y. This implies TA is 1 1. Okay. So the okay. So any other doubt? Okay, then we will go to the okay, we will go to the next problem. So the question is to check whether the statements are true or false. So first question is sum of two eigenvalues, whether it is an eigenvalue, and sum of two eigenvectors, whether it is an eigenvector. So what do you think? Is this true or any of this is true? Or you can think about examples also, like sum of eigenvalue, whether it will be an eigenvalue, and in the same way eigenvector.
Ma'am,
Yes.
sum of two eigenvalues is an eigenvalue of that same matrix.
Yeah, same matrix I am asking.
Okay. No, ma'am. First is false.
Yeah, first is false. Can you give some counter example?
If we take identity matrix.
Yes, identity matrix we can take 1 0 0 1. Okay. So here the eigenvalues are 1. Okay, 1 is the only eigenvalue. So if I am taking the sum of here actually we don't have distinct eigenvalue. Anyhow, I can take 1 plus 1 equal to 2, not an eigenvalue. Okay. Let me give an example where we have distinct eigenvalues. Okay. I'm just modifying your example. So this is, I'm just taking 1 0 0 minus 1. So what are all the eigenvalues here? So this is a diagonal matrix. So eigenvalues will be the elements in the diagonal. Correct?
Yes, ma'am.
Okay. So eigenvalues are 1 and minus 1. So sum of eigenvalues equal to 0. It is obviously not an eigenvalue because it is a non-singular matrix, not an eigenvalue. So 1 is false. Now what about the second option? Sum of two eigenvector, whether it will be an eigenvector or not. Actually, if we are taking the eigenvector, corresponding to, okay, that I will give you some exercise. Before that, here we will go with the same example. Okay. First case, we will take lambda 1 equal to 1. So what we will get is 1, 0, 0, minus 1, minus lambda I. Okay. 1, 0, 0, 1 into x1, x2. So we are just finding the eigenvector here. Okay. So from here, yeah. Any doubt?
Yes, ma'am. Second is true.
Second is true. Okay, we will check with this example. Okay.
Okay.
So what I am doing is a minus lambda I am taking a minus lambda x equal to 0. So I am finding what is the x, what is the eigenvector here. So from here I will get x2 equal to 0 and x1 can be any value. So for example, 1, 0 I can take them. Okay, 1, 0 will be an eigenvector. Now I am taking lambda equal to minus 1. So 1, 0, 0, minus 1, minus minus 1, 0, 0, minus 1. Because lambda equal to minus 1 here, okay? So this is 2, 0, 0, 0. So this is our a minus lambda I. Okay, lambda 2. So a minus lambda 2I of x equal to 0 means 2, 0, 0, 0 into x1, x2 equal to 0, 0. Okay. So from here we will get x1 equal to 0, but x2 can take any value. Correct? Here 2 x1 equal to 0 and 0 x1 plus 0 x2 equal to 0. So whatever the value x2, it does not matter. Okay. So for example, we can say 0, 1 is an eigenvector. So we got one eigenvector 1, 0 corresponding to lambda equal to 1 and 0, 1 corresponding to lambda equal to 2. So I'm adding this 1, 0 plus 0, 1 equal to 1, 1. It is not an eigenvector. Okay. So you can check whether there exists some lambda. Either like lambda, two possibilities are only there, 1 and minus 1. In any of the case, will it be an eigenvector? You can check. So before proceeding to next question, I will give you one exercise. If x, y are eigenvectors corresponding to same eigenvalue. Here we have taken two distinct eigenvalue and the corresponding eigenvector. We added those eigenvector and we got it is not an eigenvector. The addition of two eigenvectors is not an eigenvector. Now I am taking the eigenvector corresponding to the same eigenvalues. Note that this eigenvector can be linearly independent also. If x is an eigenvector, we have cx is also an eigenvector. But there can be cases y is not cx. Okay. So you should cover all those kind of things. So just check to some eigenvalue lambda. Then is x plus y is an eigenvalue. Sorry, eigenvector. Okay. So just try to solve this question. It's not so difficult. You can just try like take x and y corresponding to lambda only. Then see whether x plus y will be an eigenvector or not. Okay. Fine. Can we go to the next question? So this is a very simple question. So the eigenvalues are given, and the question is to find the determinant of the matrix A. But we have the result determinant of A equal to, or you can just say the result.
Minus 446. Minus 546.
Yeah, determinant of A is the product of eigenvalues.
Eigenvalues.
So it is, you can just calculate it using calculator. So it is minus 546. It's a very trivial question. Now, so this is a good question. Let's see. Let A be an idempotent matrix. Okay, we'll say what is idempotent if you don't know. So, given A is an idempotent matrix, then question is, what is the eigenvalue of A? Like, not what is the eigenvalue, what are all the possibility of the eigenvalue of A? Okay. So, first of all, anyone knows what is idempotent matrix?
If A square equal to A, then A is said to be an idempotent matrix.
Yeah, correct. If A square equal to A, then it is called an idempotent matrix. So, we need to check what are all the possibility for the eigenvalues of A. Okay. Suppose lambda is an eigenvalue. Okay. We need to find what are all possible eigenvalues. And here we are assuming lambda, some lambda is an eigenvalue. We need to find what is the value of lambda. Okay. If lambda is an eigenvalue of A, we can say Ax equal to lambda x. 1 minute. Okay. If lambda is an eigenvalue, we can say Ax equal to lambda x for some x not equal to 0. Correct? Now, one thing I can write is A square x. Okay. A square x is A of Ax. Okay. A into Ax. Now, option B. Actually, it's not option B. Okay.
Option A, ma'am. 0
Yeah.
and 1.
0 and 1 are the possibles. So, okay, let me prove it. So, A square x is A into Ax. And what is Ax? Ax is lambda x, correct? Now, we can take this lambda outside. So, it is lambda times Ax. Again, this Ax is lambda x. So, lambda into lambda x, which is equal to lambda square x. Okay. So, this we used Ax equal to lambda x property. Now, we haven't used this A square equal to A. Okay. Again, we are starting with the A square x. Okay. Since A square equal to A, we can write it as a square equal to a. So a square x equal to ax. Correct? Again, what is ax? Ax equal to lambda x. So we have two equations, a square x equal to lambda square x and a square x equal to lambda x. So we can equate it lambda square x equal to lambda x or lambda square minus lambda into x equal to 0. So here we have x is a non-zero vector. Since it is an eigenvector, we already taken for some x not equal to 0, x equal to lambda x. So since x is non-zero, only possibility is lambda square minus lambda equal to 0. Or what is lambda square minus lambda? Lambda into lambda minus 1 equal to 0. That implies lambda equal to 0 or lambda equal to 1. Okay, this is not AND condition. Like either of this, either can be lambda equal to 0 or it can be lambda equal to 1 or it can be both. Okay, is that clear? So we started with some eigenvalue lambda and we obtained lambda can be 0 or lambda equal to 1. Okay. So eigenvalues of A can be 0 or and 1. Okay, here what I'm saying is it can be 0 or 1 or it can be 0 and 1. What I want to say is if A is idempotent matrix, we cannot say A have both 0 and 1 as the eigenvalues. So for example, I'm taking A equal to 0, 0, 0, 0. Okay. Here A square equal to A. Both are 0 matrices. So here only eigenvalue is 0. Here 1 is not an eigenvalue. Even though it is idempotent, 1 is not an eigenvalue. Here 0 is only eigenvalue. That only we are saying. It can be 0 or 1 and both. Okay. Again, I am taking A equal to 1, 0, 0, 1. Here also A square is identity, A is identity. Here only one eigenvalue is possible, that is 1. Okay. And in other case, I am taking 1, 0, 0, 0. What is A square? A square is again A, right? Okay. A square is A. Here both 1 and 0. See, this is a diagonal matrix. We can see 1 and 0 are eigenvalues. Okay. So all the possibilities are there, but always at any for any idempotent matrix, only possibility for eigenvalue is 0 or and 1. Okay. Okay, now the next question is, so I'm giving a matrix 0, 0, 0, 0. So we haven't done a question on diagonalizability. So the question is a matrix A is given. Okay. It is actually nilpotent matrix. Okay. If you don't know nilpotent, just leave it. So the question is under what condition? Like under what values of A and B? If we are giving what values A, B, C, then it will be diagonalizable. Okay, is the question clear? So we need to find the value of A, B, and C such that A is diagonalizable. So first of all, we will start with what is the characteristic equation and the eigenvalue and eigenvector, and we will go. Okay, so determinant of A minus xi. So we can write it very easily because almost everywhere it is 0. Only along diagonal we need to write minus x, and this ABC will remain like that. Okay, minus x 0 0. So without writing also actually you can write, since it is a diagonal matrix. 0 b minus x 0 0 0 c minus x. So this is a minus xi. We need to find the determinant of this. Okay, what is this? X power 4. Okay, since it is a diagonal, some triangular matrix, the only thing we need to find the determinant is just multiply the diagonal elements. Okay, so this is x power 4 equal to 0. So we are equating this x power 4 equal to 0 to obtain the eigenvalues. So we got only one eigenvalue for this matrix and it is 0. Okay. Now, when it will be diagonalizable? So for diagonalizability, we have one condition. Okay. So A is diagonalizable if and only if
If and only if there exists n linear independent eigenvectors.
Yeah, n linearly independent eigenvectors, correct? Okay. So here actually, we have only one eigenvalue. So whatever the eigenvector we are having, that eigenvector is corresponding to this eigenvalue 0. Okay. So if x is an eigenvector, it is corresponding to eigenvalue 0. Okay. So this condition should be satisfied. For some x non-zero, a minus 0x equal to 0. What does that mean? Ax should be equal to 0 for x non-zero. Okay. So what actually we want here? A is diagonalizable if and only if A has n linearly. So here n equal to 4 because A is a 4 by 4 matrix. So here we can n equal to, it has n equal to 4 linearly independent eigenvectors. Okay, 4 linearly independent eigenvector we need. So what we are saying is we need 4 linearly independent x such that Ax equal to 0. Correct? Is this possible? 4 linearly independent eigenvectors for Ax equal to 0?
Yes, ma'am.
No, because what is A? C. A is the matrix which is having rank. Okay. It is possible, but under what condition it is possible? See, if A, B, C are 0, it is possible. Otherwise, it is not possible. Okay, let me explain a bit more. Okay, see, we need 4 linearly independent eigenvectors such that Ax equal to 0. So what are all these 4 linearly independent eigenvectors? These 4 linearly independent eigenvector means these vectors will generate whole R4, right? Okay. 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 See, what I'm saying is we need 4 linearly independent eigenvectors such that Ax equal to 0. So 4 linearly independent eigenvector means all the vectors. This A is a map from R4. Okay. A is a 4 by 4 matrix into a 4 by 1 matrix we are doing. That X means it is a 4 by 1 column. Okay. So Ax equal to 0 for all X actually. For all linearly independent eigenvector means, for example, if we are taking any x1, x2, x3, x4, we can write Ax equal to x1 into A1000 plus x2 into A0100 plus x3 into A0010 plus x4 into A0001. Correct? Okay, let it finish. Okay, so I'm taking any vector from R4. So this, I can write it like this, x1 into, I'm just writing it as using the linearity property. Okay, now if each of this Ax equal to 0, okay, these 4 are linearly independent. If each of this Ax equal to 0, finally we will get this is equal to 0. Okay, now if we have 4 linearly independent eigenvectors. Suppose y1, y2, y3, y4. These are all vectors. Okay, are linearly independent eigenvectors. Okay. Now, for any y in R4, we can write it as y equal to okay, I'm taking 4 linearly independent eigenvectors. Since it is linearly independent and there are 4, so this generates whole R4. Okay, so for any R4, we can write it as A1 y1 plus A2 y2 plus A3 y3 plus A4 y4. Okay, since yi are linearly yi are eigenvector, we can say Ayi equal to 0. That means A minus 0 I into yi. Okay, yi is the eigenvector corresponding to 0 because 0 is the only eigenvalue. Okay, so Ay equal to 0. And what will be Ay? AY equal to A1 into AY1, A2 into AY2, A3 into AY3 plus A4 into AY4. Since this side is completely 0, AY is actually 0. Okay. So, now what I am saying is, if we are getting 4 linearly independent eigenvectors such that AX equal to 0, this basically says that AY equal to 0 for all Y in R4. Is this statement fine now? Is this statement okay for everyone? Any doubt? If you have any doubt, I can repeat. Okay. So we are taking Y as the linear combination of these 4 linearly independent eigenvectors. Since the eigenvectors, for eigenvectors, X equal to 0. So AY is also 0. Okay, since AY we can return as the linear combination of the eigenvectors AX1, AX2, AX3, AX4. So each for each Y in R4, we are getting AY equal to 0. Okay. So what does that mean? All the element in R4 belongs to the null space of A. Okay. The whole R4 belongs to the null space of A. Okay. So nullity of A equal to 4. That implies rank A equal to 0. So when will rank A will be 0? All the elements are 0. All the entries in the matrix A are 0. Okay. So that means the A equal to B equal to C should be equal to 0. Fine. Okay, I will just repeat once again. So this is the matrix A, which is having A, B, C here. All others are 0. First, we are finding the characteristic equation or characteristic polynomial of this. And we got the characteristic polynomial as x power 4. So we are equating this to 0 to obtain the eigenvalue. Okay. So we obtain x equal to 0 is the eigenvalue. So whatever the eigenvector we are taking, it will be corresponding to this eigenvalue because we have only one eigenvalue. Okay. Now, A is diagonalizable if and only if A has 4 linearly independent eigenvectors since dimension of A is 4. Okay. Now, A has 4 linearly independent eigenvector means if we are taking any element from R4, that element can be written as the linear combination of these 4 linearly independent eigenvectors since R4 has dimension 4. Okay. So, any Y can be written as A1 x1 plus A2 x2 plus A3 x3 plus A4 x4, where x1, x2, x3, x4 are eigenvectors corresponding to the eigenvalue 0. That means AXI equal to 0 for each I equal to 1, 2, 3, 4. So AY equal to A1 into AX1 plus A2 into AX2 plus A3 into AX3 plus A4 into AX4. So each AXI equal to 0 means the right hand side is 0. So AY equal to 0 for any Y in R4. That means for any Y in R4 belongs to the null space of A. Like when we operate A to any Y in R4, it is going to 0 means Y belongs to kernel of A. Okay. So this A has nullity 4. Okay. Nullity means dimension of the null space. It has nullity 4. So by rank nullity theorem, it has rank 0. Rank 0 means obviously all of the A, B, C should be 0. Okay, this is the matrix. So all of this should be 0. So if A is diagonalizable, all ABC should be 0. Is that okay? Anyone is having doubt in this?
No, ma'am.
Okay. So I think let's stop the session for today. So, okay, in any of the question, if any of you have doubt, you can ask. Otherwise, we can stop the session. Okay. Okay, so this is the last week question. So we are stopping here. So thank you for everyone for joining, and sorry for the some inconvenience caused. And I know so the participants are less today. Anyhow, I will upload this in the YouTube also. Everyone can watch if they needed. So, okay, then thank you everyone. You can leave the meeting. Thank you all.
Thank you, ma'am.